So welcome back. Today we'll be discussing Shor's algorithm, and in particular we will be setting the stage up, which means we will be introducing a few key concepts that will be required to understand the algorithm. First, we will be motivating a little bit why this is a very important algorithm by introducing what public key cryptography is. And then we discuss a little bit about factoring numbers, introducing a few of the basic ingredients that we will require later on. So to motivate the importance of factorizing a large number, let us talk a little bit about public key cryptography, which is a way of performing safe communication in public channels. Now suppose that we have our two usual suspects, Alice and Bob, and they want to communicate in a safe way. Now Alice has a public key that can give Bob, and Bob can encrypt this message by using this public key. So in public key cryptography, Alice publishes a public key that then Bob uses to encrypt the message. And then Alice uses a private key to decrypt the message. This encryption relies on the asymmetry of cryptography. It's very easy to encrypt a message just by multiplying the message by a very large number, but it's very difficult to decrypt it because it's very difficult to factorize the resulting number into its main factor. This relies on the concept of one-way function that we'll now discuss in a bit more detail. One-way functions are functions that are easy to perform and hard to invert. In particular, in the case of public key cryptography, multiplication is an easy thing to do, while factorization is very hard. This can be seen by the fact that the best known classical algorithm that can factorize number, that is the number field sieve algorithm, scales roughly as exponential of n to the power 1/3 for an n-bit number. We will see that quantumly there is an algorithm, that is Shor's algorithm, that scales polynomially with the number of bits. In particular, it scales roughly as n to the power 3. Now, before tackling and before seeing the Shor's algorithm, we need to introduce a few basic ingredients. The first one is the great common divisor, S of two numbers A and B. This is the largest number, integer number, such that A and B can be decomposed in this way. In particular, a notation that we will introduce is that if S is equal to 1, then A and B are said to be co-prime. Finding the greatest common divisor of two numbers is actually something that can be done very efficiently in classical algorithm. And there is the famous Euclid's algorithm that efficiently computes the great common divisor of two numbers. Another very important ingredient that we will need to introduce for Shor's algorithm is the order of a number modulo another number. Let's take two positive integers, x and c, such that x is lower than c. The order r of x modulo c is the smallest positive non-trivial integer, such that x to the power r is equal to 1 modulo c. Now, let's see the complexity of finding the order r of x modulo c. Classically, this is a very hard problem, while quantumly, there's an efficient subroutine of Shor's algorithm that computes this by utilizing the quantum phase estimation algorithm. Now, why is this relevant for the factoring problem? Indeed, it turns out that factoring and order finding are very much related to each other. Let's see how. If you want to factor a number c, knowing the order r of x modulo c, the problem actually simplifies quite a lot. So if we know the order r, then we can rewrite the definition of the order in the following way. So x to the power r minus 1 modulo c is equal to 0. This is very important because if r is an even number, then we can decompose this. You can decompose this equation by considering that x to the power r squared r over 2 minus 1 times x to the power r2 plus 1 modulo c is equal to 0. If it's odd, if the order R is odd, actually we need to fail. We fail and we need to start again. But if R is even, then this equation tells us everything that we need to know. In particular, if the order x of R over 2 is equal to 1 modulo C, we would have problems because one of these two terms would be 0. But actually, this cannot be, and this is just because of the definition of the order. But what can be is that we will find that x to the power R over 2 is equal to -1 modulo C. In this case, actually, we cannot say anything about the factorization of C, and we fail to find what the factors are. If we are not in those two situations, actually we are done. So we know exactly what the factor of C are. In particular, the fact that we can write this equation, it can mean that the product of x to the power R over 2 minus 1 times x to the power R over 2 plus 1 is directly equal to C. In which case, we already know directly the factors of C, which are these two terms over here. The other case that can happen is that because this is an equation modulo the large number, it can happen that the product of those two factors is equal to k times C, where k is just an integer number larger than 2. In this case, we are guaranteed that the great common divisor of either x to the R over 2 plus or minus 1 and C is a factor of C.